This is Guangshan Bao from Westlake University. I'd like to present our work, Target-Side Data Augmentation for Document-Level Machine Translation. Previous data augmentation methods in machine translation mainly focus on source-side augmentation because a synthesized target usually downgrades the autoregressive modeling of the target sequence. Previous methods can mainly be categorized into two types. One involves monolingual data, translating monolingual text to its source or target language using forward or backward translation. Another leverages pre-trained language model or paraphraser to paraphrase existing corpus to generate augmented data. These methods rely on external data or model. In comparison, our method relies on the given parallel data only. We introduce a data augmentation model to generate new potential translations of given parallel text. This data augmentation model is also trained using the same parallel data. Specifically, our target-side data augmentation involves three steps. In step 1, we train a DA model, given sample xi and yi from the data distribution. We model the posterior distribution of possible translations of xi. After training the DA model, in step 2, we use the DA model to generate new possible translations, y hat, for each training sample, obtaining augmented data. In step 3, we use this augmented data to train a traditional machine translation model. The augmented data represents a smooth distribution of possible translations. Therefore, the MT model approximates this distribution and obtains improved performance. The DA model estimates the posterior distribution of possible translations, y given observed xi and yi. Since yi is used as the condition and also used as the training target, we cannot directly model it. We introduce an intermediate latent variable z to separate the condition yi from the training target, as the equation 1 shows. By sampling various z from its distribution, we can approximate the expectation over z in equation 1 as the sample average in equation 2. As a result, we obtain an approximation of the MLE loss as equation 3. Using Jensen inequality, we get an upper bound of the loss, which can be easily optimized. We match the output distribution of the MT model to the distribution of the DA model as the equation 5. We sample several translations from the DA model in equation 6 and approximate the loss for machine translation using the sample average in equation 7. The DA augmentation process starts with A parallel data. We extend SI with latent Z to generate B extended data with latent Z. The latent Z is sampled engrams from YI, which is also token sequence. We append these tokens to the end of the XI using a special token OBS to separate them. Using this extended data, we train the DA model. The input sequence of this extended data is as C extended input. We pass this extended input to the trained DA model to generate D potential translations. Pairing the original XI and the new potential translations, we obtain E augmented data. Target site augmentation significantly improves both sentence level transformer baseline and document level G transformer baseline. For example, it improves the BLUE score on news by more than 2 points. When target site augmentation works with back translation, it further enlarges the improvement to about 3 points on news. We demonstrate that the posterior distribution of the DA model performs much better than the prior distribution. Specifically, it gives lower PPL and balanced diversity and deviation. We further observed that the latent variable determines the deviation and diversity, where a balance between the two metrics is key to the model performance. That's all. Please check our paper for more details. Thank you.